normalized gamma, or I'm going to follow the uniform decision making by gamma. Okay? So this is the formula, and this will give you the probability of choosing each arm. Okay, so what happens? So we choose an arm, we play the arm, we see the reward. Okay? So now we update the weight. And the way we update is the following. So we're going to choose something called a pseudo reward. So we're not going to use the one we see, but we use something a little bit different. So we take the reward we see, we divide it by the probability of choosing that arm. If we decide to choose that arm, otherwise we keep it 0. The nice thing of this is the following. It gives you an unbiased estimator of the reward. Okay, so if you do the math a little bit, then you see that there are two cases. You choose an arm, you don't choose an arm, right? So the probability of choosing an arm is P. So you take this value, you multiply by P, you get this value. Otherwise, if you don't choose, you get 0. So this value plus 0 is this value. Okay? So then it means that in expectation, this pseudo reward gives you the true reward.
So it's kind of like calibration for this.
Yes, but the reason we do this calibration is the following. So why we need to do this calibration? Because now, if you think about the whole thing, it has nothing to do with stochasticity. It has nothing to do with statistics. So you cannot use statistics to infer about all the actions if you just use this value, because they have nothing in common. They're not correlated at all. It can be completely arbitrarily random. But if you do this thing, then in expectation, for all the arms, even for the arms you haven't put, in expectation, you get an unbiased estimator. And that's a beautiful trick. Because now, you can choose your randomization to fool your opponent. Whatever you do here, in the end, it gives you an unbiased estimator of the underlying reward. So you can use this, in theory, you can use this now to infer. That's the beauty of it. Okay?
Just one quick comment. It looks like a hidden CNC for me. It's like more like a hidden CNC.
Yeah, if you go that direction, then you can claim in similarities. Yes. It's not exactly, but yeah, but you can think of something like that. Yeah. So once you have this unbiased estimator, so what you do next is to update the weight by an exponential term. Okay? So that's why it's called exponential weight updating or exponential exploration. Okay? And using this exponential weight update, kind of like a very aggressive way to focus on the best arms in hindsight. So for example, you have 3 arms like this. As you go, you will learn that the arm one could be, the best it fits in hindsight. So you put lots of weight there, very quickly. That's why it's exponential. Okay?
You say that it's kind of unbiased estimate of what?
Of the underlying reward.
But the reward is changing over time, right?
Yes, exactly. But this is a nice thing.
I mean, like
so first of all, it can be deterministic. There's nothing to do with the previous year. It changes over time. No statistical properties at all. So ideally, if you just do it directly, try to learn, you end up learning nothing because there's nothing in common. But if you do this trick, then what you do is you introduce statistics into it. And this statistics is nice because this statistics has a very nice behavior. It has, in expectation, it will give you something like this. So if you're familiar with stochastic optimization, for example, sometimes you see that adding random noise to the model actually helps. Maybe have let me.
The reward is deterministic. The reward is deterministic, but the process is stochastic.
Yes, yeah, exactly. So you introduce the stochasticity into it. And that's nice. Let me draw something. So if you are, yeah, I think I still need to light. Okay, sorry. So you are familiar with stochastic gradient descent, right?
Yeah.
So you want if there's a function, you want to calculate the gradient.
Yeah.
You want to calculate the gradient. But many cases you cannot calculate the gradient because it's either computationally difficult or whatever. But you still want to calculate the stochastic version of it. Okay? So stochastic gradient descent is actually is a stochastic one-dimensional move, right? But in expectation, it will give you the true gradient. How can you do that? You randomly sample from the neighborhood. You choose one point, you take the difference, you take the line. And if you do it wisely, the way you sample from the neighborhood, first way this is uniform random, then in expectation, this line can be, if you just take one single instance, it can be very random, very hectic. It can be this. It can be anything. But in expectation, it will give you the gradient. Something there very similar happening. Okay? So you don't know what the correlation. If you don't see the value, you should not have any information about it. But because you move the whole thing into a stochastic process, you take the expectation and you know that in expectation that this should be the value, even for those values that I haven't seen. And now you move to the probability space, and you do all the calculations in probability space. Much more convenient. Yes, because expectation.
The rate of conversion evaluation, the rate of conversion of this stochastic process to the conversion.
Yeah, it can be squared. Yeah, this will be something there. Okay, so here's explanation. Thanks to what I just said earlier. Updating the weight. Exponential growth makes us focus more on the better arm splitting. And the last one, but I'm not going to prove this because I don't think so. We have enough time because it's more complicated. But now we can prove that because we introduced the kind of stochasticity into the model. Now within the probability space, we can do nice estimations, and we can prove that the grad now is sublinear, is square root of t. Okay? So we can learn. So it means that we can learn the specific strategy in hindsight. We can converge to it. This is a very nice. Even nicer, we can show that this is one of the best possible. Because again, the lower bound for the regret, the external regret, in this case is also square root t. So you cannot do better than square root t. You can still play around with all the coefficients like k, because here we have k low k, and here the optimal is low bound is just square root k. So x3 still has a low k, but you can get rid of it by using all the algorithms. So there's limited most, quite a few more. So you can get rid of the low k. But usually, if you only care about t, then square root t is optimal. Okay? So any questions about F3?